In this video, I'll introduce the law of exponents. But before we discuss the law of exponents, let's talk a little bit about repeated addition. If you think for just a moment what the sum total of 5 plus 5 is, you know quickly that that answer is 10. Even if I asked you 5 plus 5, you could quickly add that to equal 15. But after about the fourth or fifth number being added together, the addition becomes a little bit more tedious to complete. Often in our mind, we'll add two groups of these numbers together. This pair of 5s makes a 10. This pair of 5 makes a 10. Those two 10s go together to make 20. Hopefully you recognize that each of these repeated addition problems can be simplified with the expression written in the form of multiplication. Now, just like multiplication is a shorthand form of addition, repeated addition that is, exponents, integer exponents for that matter, provide a shorthand device for representing repeated multiplications of real numbers. So what we have with our exponents is that some base value a and its exponent n represent the multiplication of a repeated n number of times. So a would equal, a to the nth power would equal a times a times a, etc., a total of n times, or for n factors. So from this definition, we see that a to the first power is the product of a written one time, multiplied one time. A to the second power would be the product of a multiplied twice. A to the third power is a multiplied 3 times in a row, whereas a to the fourth power represents the product of a with 4 factors, and so on and so forth. This notation is simply a shorthand way to write this mathematical calculation. We have several rules written inside of the law of exponents, and we're going to talk a little bit about each of those rules here for the rest of the video. Now the product rule looks something like this. With a base a and a power m, or exponent m, when that base of a and its power m is multiplied by another exponent with a base a and a different power n, as long as the two bases match, then we know the result to this expression would be that base and the two powers summed together. Now let me show you why this rule works with a couple of examples. Let's suppose that I have a to the third power, and I'd like to multiply that with a to the sixth power. And I'd like to simplify that with a to some single power. You should recognize that a to the third power is the exact same as writing the product of a multiplied 3 times. A to the sixth power would be the product of a with 6 factors. Within each of these grouping symbols, there's nothing else that I can do to simplify them. So this expression could be rewritten as a times a times a, this first group of 3, multiplied by the group of 6. And as we take a look at this result without our parentheses, we see that it's simply a group of A's, I should say a product of A's with 9 factors. Since there are 9 factors total, we can abbreviate this by definition as A to the 9th power. In a similar fashion, we have a quotient rule of our exponent law. And that states that with the base A and its power m, if that's being divided by another base A with a factor n, that result could be simplified as A to the m minus n power. This could also be written as a fraction, A to the m power divided by A to the nth power also equals A to the m minus n power. But again, in order for this quotient rule to hold true, our two bases must match. If we look at this example with a concrete set of values, let's say that we have A to the 5th power divided by A to the 3rd power. Well, we could rewrite that as A multiplied 5 times divided by A multiplied 3 times. And you should recognize that when two products are being divided by one another, their factors can cancel as long as we have a match from the numerator to the denominator. And in this case, 3 pairs of our A values cancel each other out. They factor with one another. That leaves us with A times A, which is also A to the 2nd power. Or in other words, A to the power 5 minus 3. For our power to power rule, we explain the shortcut for taking a base with an exponent that's raised again to another power. Let's investigate this with concrete examples before we find our solution. Let's suppose that I have A to the 3rd power that's raised again to the 2nd power. Well, we know by definition of our exponents that A to the 3rd power would be a number raised to the 2nd power. So when we raise a number to the 2nd power, that would be just like multiplying it by itself twice. A to the 3rd power times A to the 3rd power. And from our product rule, we see that A to the 3rd power times A to the 3rd power is A to the 6th power. What if I try a base? Let's use a different base value this time. B to the 4th power immediately raised to the 5th power. Well, again, we have a number inside this parentheses that's being raised to the power of 5, so B to the 4th would be multiplied by itself 4 times in a row. When utilizing our power rule in pairs, we see that B to the 4th times B to the 4th is B to the 8th power. And again, B to the 4th times itself is B to the 8th power. Now we can utilize the power rule one more time to see that our result, whoops, I forgot one. This was B to the 4th to the 5th power. We need an extra one over here, so let's include that, times B to the 4th. Now B to the 8th times B to the 8th power is B to the 16th, and when we multiply that times B to the 4th power, we obtain our final result of B to the 20th power. So look closely here. What did we do to turn the numbers 4 and 5 into the number 20? What did we do to change the numbers 3 and 2 to the number 6? Well, hopefully you recognize that you multiplied those together. A to the mth power, quantity raised to the nth power, is simply equal to A to the power of m times n. That's our power to a power rule. Let's take a base, this time x, and raise it to the 6th power, and immediately divide that by x to the 6th power. What does our quotient rule tell us that the result of x to the 6th divided by x to the 6th should be? Well, hopefully you recognize that this would be x to the 6th power minus 6, and 6 minus 6 is 0. So this x to the 6th divided by x to the 6th is really equal to 0. Let's think about this a different way. What happens to a fraction when its numerator is the same as the denominator? Do you notice that that's the case here? Its numerator is the exact same as our denominator. As an aside, I'll remind you, maybe if we think of the fraction 5 over 5, or 2 over 2, or 3 over 3, what happens to each of these fractions when the numerator is the same as the denominator? Well, hopefully you recognize that when the numerator and the denominator match in a fraction, the fraction itself reduces to 1. So by way of comparison, any time that x is raised to the 0 power, it too is simply equal to the number 1. Again, this is because x to the 0 power could have been written with any value of exponent here. If I had x to the 15th, that would be 15 minus 15. End result is 0. It too reduces to 1. So our 0 power rule simply is x to the 0 power is equal to 1. Or better yet, to remain consistent here, let's use the letter a again for our base. The base a raised to the power of 0 will always be equal to 1. Up until now, all of our exponents have been positive. But I'd like to talk about what happens in the event that our exponent is actually a negative integer. When you see a negative exponent, I want you to think of the word reciprocal, because in mathematics, the word reciprocal means to flip a fraction. And to flip a fraction is the appropriate change to apply to a negative power problem. As I mentioned a moment ago, all of our exponents up until now were positive integers. And up until now, the results of all of our positive integers were a series of multiplications. With a negative exponent, feel free to think about that as a series of divisions. So in other words, a to the negative m power is equal to 1 divided by a to the positive m power. These are reciprocal fractions due to the negative power rule. For example, if I present to you a to the negative 2nd power, you can immediately think of its reciprocal, 1 divided by a to the positive 2nd power. A to the negative 4th power is the same as 1 divided by a to the 4th power. And consequently, if we take a base with a negative exponent, if that base with the negative exponent is already in the denominator of a fraction, for example, 1 divided by a to the negative 2nd power, then its reciprocal would be a to the positive 2nd power. 1 divided by a to the negative 4th power is simply a to the positive 4th power. Sometimes you'll hear teachers explain that a negative exponent moves a base with that exponent from one side of the fraction bar to the other. So in this case, we're bringing it to the top and essentially creating that same fraction over 1. Or in these examples over here, we could have thought of them as fractions over 1, and this a to the negative 2 power moves to the other side of that fraction bar, and it moves down below. This concludes our introductory set of notes to the law of exponents. There's a lot of information presented here. We will practice with these the rules within the law of exponents throughout the rest of the week. If you have access to the electronic textbook, I recommend looking at page number 22 for additional help. Thanks for watching.